First of all, thank you for the invitation, and it's a pleasure to be here. And it's been a while since I was in front of a super technical audience like this, so we'll see how this goes. So, at Halliburton, we are looking at how we use AI broadly. It's hard not to look at it. You know, with the Nobel Prize in Physics in 24 went to two people, highly deserving people, who are not physicists, but AI people. And so I personally actually have mixed feelings on this. I wonder how your physics department feels about it. But AI is here, it's important, and when applied properly, I think it will bring a lot of value. So I'll give you a glimpse of what we're doing, at least in the field of geosciences. So in geosciences, of course, you all know this, geology is super complex, and depending on which length scale you work at, sort of determines which physics you might want to use to model it. And that all sort of translates to creating maybe big physics models, which might be problematic to deal with. So that's sort of one point to remember. The second is that, as you all know, that especially seismic, but all kinds of geosciences, geophysical data is increasing in size. We have lots of it, and it's getting larger and larger, these data sets. So you wonder, you know, we might be able to augment the physics with data and things like this. And of course, the third is compute advances. It's clear that, you know, today's compute capabilities enable a lot of things which were not even possible 10 years ago. So the confluence of these three things is really allowing AI to, you know, to make an impact in the geosciences today and other aspects of the business as well. The way we look at the value that AI and ML might bring, at least in the geosciences, is twofold. On the left, for example, it's an efficiency play. You know, doing interpretation of seismic, for example, is prone to bias, it's manual, it's painful. You know, and so if properly done, you could use AI techniques to speed up that process, remove bias, and, you know, enable consistency and things like this. So it's purely an efficiency play. And then more importantly, on the right-hand side, just because the sheer massive amounts of data, which is impossible for human beings to consume at scale, AI techniques will allow us to really mine this and look for hidden insights which might be missed by traditional means. So I think these are the two areas we feel, you know, is where AI brings value. We're looking at AI in many different sort of areas as shown in this table. And I don't know why it says top three, there's more than three, but in all of these use cases, we are exploring how AI can be used. And a lot of these techniques actually are in commercial products that we are now beginning to sell. So I'll just give you a glimpse of a few use cases. This is an interesting one. You know, we have a group in our landmark division called Neftex, which does geology. In fact, they have a huge data set, public and private data set on the geology of the Earth. And so there's huge amounts of geological data and geological models. And so the idea is that in some cases, there are gaps in our understanding of geology. How do you fill those gaps? Traditionally, geologists fill it literally by drawing lines and such. And so the idea is to explore the use of AI, in particular, things like generative networks to help fill in the blanks, so to speak, in geology. And so this technique is surprisingly powerful and is helping, you know, us and our customers a lot in filling gaps in geology. This is, of course, pretty routine nowadays, seismic interpretation. And this is purely an efficiency play, consistency play. And so lots of people are doing this. We are as well. And this is becoming pretty routine to use supervised learning-based AI to do interpretation. We're also using some of these techniques to do inversion or augment the inversion process itself in seismic, and with surprisingly good results. And we find that when done right, when trained right, it reveals a lot of things which were previously missed by traditional means and things like this. So it's a powerful use case for sure. This is again an example or a use case of filling in the blanks. Often in lots of fields we find that we don't have seismic or poor seismic, but we might have a lot of logs. And so how do you then connect all of this in a systematic way? And so I think AI-based techniques are a powerful way of connecting and interpolating and these logs and sort of help build the Earth model out of it. This is for production reservoirs, mature fields and things like this. A lot of reservoir models, the traditional ways of doing reservoir modeling is to do history matching with production data and so on. But if you look at sort of the inputs or the information that's available in a given mature field, things like seismic, logs, production data, etc., when you do history matching, to get a result which respects all of this data at any time is a challenging exercise. So you need a sort of a different way to assimilate all of this data to do history matching or make the model comply with all of this information simultaneously. And so we're exploring, these techniques of using graph networks and things like this to to create ensembles of models which respect the data, not just at one time instant, but at all time instance as you get more and more production data, for example. And so this is early days on this, but this is sort of a very powerful technique that we're finding for use in mature fields. Let me just switch to a different set of use cases. We, of course, do a lot of well logging. And here, too, AI plays a strong role. I'll just sort of give you a sense of it. In all of the well logging modalities, if you use resistivity or acoustic or nuclear or sonic, effectively, underlying it is the classical inversion problem, where the forward model is generally a PDE, or and then you do the inversion either in a classical sense or in a Bayesian sense. Either way, it requires that you have to run these forward models, and these forward models tend to be large. And then if you want to do real-time inversion, which is what you want to do with logging, either you have to log slowly, which nobody wants, or you do post-processing, which nobody wants. So everybody wants inversion to be done in real time when you're logging super fast. We're drilling faster and faster every day, and so while logging while drilling, the game is to do inversion in real time. And so this is where neural networks play a key role. In all of these kinds of cases, as I mentioned, we're trying to approximate the forward model PDEs with neural networks to enable inversion. So again, as I said, we do both kinds of inversions, deterministic and statistical. In each case, the forward model is huge. And in many cases, you cannot do real-time inversion. It's so big. So just to give you a sense of the size of these models that you have to solve in terms of the matrix size that you have to solve once you discretize. And so you need to do something different. And we're using different techniques to do this approximation of the forward model by neural networks. And we are applying this actually commercially. We're using these things commercially in resistivity tools and ultrasonics and things like this. I'll give you a quick glimpse of some of these kinds of things. So this is sort of the forward model approximation with these FNOs, Fourier neural operators. They are super powerful and for approximating PDEs. And there's upfront cost to train them in your domain of interest. So for example, if you're using this for electromagnetic use cases, across different formation types and things like this, you have to make sure your training sets span all possible formations you might expect. And then once you do it once, then you're done. Then the speed up is dramatic. So this is an example of a three-dimensional EM electromagnetic tool for resistivity. But just give you a sense, on the left, pictures show you the amplitude and phase of this FNO prediction versus the classical PDE solver. There's essentially no difference. But the speed up is dramatic, 0.05 versus 80 seconds. This sort of speed up enables real-time inversion during high-speed logging, and that's really what this is about. Similarly, this is an example of looking through multiple layers of casings to detect corrosion from within the well. And it's a tricky problem, but here too we are approximating the forward models with FNOs or neural networks of some kind. I don't remember exactly what. Again, dramatic improvements in speed, in compute speeds. Similarly, on ultrasonic cement evaluation-based tools, same sort of thing. So, with these kinds of speed up, it just reduces logging time, increases logging speed, and so it translates to real business value. In petrophysics, for example, since we have so much data, you have traditional closed form equations which are used in classical petrophysics. And so the idea here is to use a lot of this data to augment some of these closed form formulas and stuff like this with regressions, symbolic regressions, and they work surprisingly well. And so in many cases, we are developing these symbolically regressed petrophysical formulas on a formation by formation basis. So especially in the Middle East, we do a lot of work where we fine-tune these formulas for specific formations, and it works quite well. This is an interesting example of using, again, generative type of AI for translating models trained on, let's say, Gulf of Mexico to Norway. So, oftentimes data is limited, and, if you train something on one data in one formation, how you translate to the other or if done naively, it generally fails. So this approach of using like these VAEs, variational and auto encoders and things like this, effectively solves this problem or attempts to solve this problem by viewing, let me see if I have a, yes. So if you have, in this, I should explain this a bit better. So typically, what we're trying to do here is to eliminate sonic. You know, sonic logging is important to understand the mechanics of the formation, Young's modulus, Poisson's ratio, and things like this. But it's expensive. For example, in North America, nobody wants to run sonic. So what do you do on the left picture? You have a poor man's sonic. So you have drill bits which are censored with accelerometers and strain gauges and things like this. And so can you then invert this data to say something about Young's modulus and Poisson's ratio of the formation? So hence poor man's sonic. In principle, you can approach this problem as a physics problem. You know exactly how this should translate, but it doesn't work quite well. So, or it needs to be grounded because you just do not have enough information to do it. And so the idea here is to use these kinds of models, these generative models, to effectively look at the vibration, ROP, strain gauge data, sort of as random variables, and learn the joint distribution of these things through these VAEs, and then use all of this information to help translate or calibrate the physics, which are quite well known from a bit-rock interaction model physics to different formation types. So techniques like this are surprisingly powerful, we're finding, and it solves a real problem, where people don't want to use sonic because it's expensive, and so you can use cheaper sensors, bits, to actually learn something about the formation while drilling. So I'll just pause. In each of these topics is, we could talk about at length, but I just wanted to give you all a glimpse of the kinds of things that us and our peers as companies are also doing. So thank you.
Fascinating work, Sri. I want to open it up to questions from the audience.
So what does it have to do with the energy transition on this?
Our view on this is as follows. We are, as an oil and gas service company, we are super active in CCUS projects and in geothermal projects. So these are near adjacent to CCS, sequestration. So since we're talking about this, for example, we're doing work in the area of material science, because a CO2 well, a completion system for CO2 sequestration has a lot of material science challenges. Number one, in cement. Portland cement and CO2 don't go well. CO2 plus water, carbonic acid attacks Portland cement, potentially degrades it. So we're doing a lot of work in the area of cement or Portland cement and what happens to it over 100 years with CO2, and what are non-Portland cements, for example. The other thing is elastomers. Every completion tool system and every well in a CCUS well will require completion systems are filled with elastomers, seals and stuff. Again, rapid gas decompression, things like this will literally explode these seals potentially. So you have to really do some new material science to really make sure that the seals will survive supercritical CO2 and things like this. CO2 plume migration, CO2 plume monitoring, these are things that we are doing. I mean, a lot of things that we do, information evaluation, seismic, fiber optic sensing, EM fiber optic sensing, the combination thereof. These are all techniques that oil and gas has proven and are directly applicable to CO2 sequestration. In geothermal, since I'm on a roll, in geothermal, we're doing similar things. I know that you have a talk with Fervo later today. And so, for EGS systems, we're doing a lot of work, also with Fervo. But we're also looking at pumpless geothermal, meaning that super deep drilled wells such that you have a thermosiphon effect, so you don't need pumps, which is really, I think, is what would be a game changer for geothermal. And so for that you require completely unknown drilling technologies. The tradition, if you're doing basement rock drilling for like 10 miles, the traditional diamond bits will not work. It would be uneconomical to drill like a heat exchanger of wells that deep. And so we're working on electric arc drilling, for example. So there's a lot of things that the oil and gas, a traditional oil and gas company like us are at least working in these two spaces. Just to give you a sense of what we're doing.
Yeah, just a different kind of question, which is more about your team. As you are doing this kind of work now, has the number of people on your team shifted, and how has the skill mix shifted? And then a second question is, as you think about advice you would give researchers at Utah and U of H, what kinds of areas are you finding most helpful in terms of work places like Utah and U of H are doing?
Yes, thank you, great question. So I think from a skills perspective, just to give you a sense of we have about 2,100 engineers and scientists, of multiple disciplines, of course. So the bulk of and if you track the makeup of this, we have about 800 or so mechanical engineers, and this has been steady because our business is hardcore tool development and stuff. And so that's going to always be big. 5 years ago, the next big group would be like electrical or the geosciences, but now it's software and data science type people. So, so digital automation, data science, AI, is causing us to actually hire more people in this area, for example. Although, we much would prefer that to me, every engineer is by definition a data scientist. And so our approach is to actually have our regular engineers and scientists become data scientists. So in that sense, we are training a lot of our people to become one. To me, it's not rocket science. It's something that good engineers already know, statistics and stuff like this. So yes, I think we're hiring more doing more software, more digital, more AI and things like this. When it comes to AI, I wouldn't say that we're doing fundamental things like coming up with dramatically different neural network architectures or training pipelines or things like this. We are mostly applying it. So, there are lots of people in the world doing cutting-edge research in neural networks. So I think translating all of that cutting-edge research, which is happening in so many industries, to our context is where we are focusing. All of these use cases is how do you use VAEs or generative networks or graph neural networks, and for our use case, this is our sweet spot. And if you ask me, especially in the area of AI and the geosciences, what should you do from a research perspective? It's exactly this. I think we are finding that traditional, the architectures that Google and the others work on may or may not be directly applicable, for example. And so I think much work has to be done to, fine-tune these foundational neural network and other architectures for this context.
Any other questions? If not, let's give a big round of applause for